got bulk. I'm gonna have like 2 more plates during 5th hour.
That's if there's any more. I get lunch first. I get lunch with my cart.
We'll give you the best chance of being successful in giving your grade type stuff.
Alright. 1, 2, 3, 4, 5. Sure. Go ahead.
I have the perfect answer for that one. Would be the coolest job to have.
Mr. Graham, I have no school this Friday, correct?
Unless we get a snow day between now and then.
What if we get snow tomorrow?
If we get it doesn't matter if we get snow. We have to get a snow day. Have to get a snow day. All right. Lucy, let's go make up that one quiz you're missing. We'll go next door. So just bring your periodic table and something to write with.
It wasn't hot enough though.
Oh, you didn't get
You're
that much
complaining
time.
about free food that you got.
Whoa, no. No. I warmed up for like a minute. That was so good. Miss Dart, I just had the best breakfast ever.
What?
I just had the best breakfast ever. Chicken, mac and cheese, mashed potatoes and gravy.
But he's complaining about it because it wasn't hot enough.
Whoa. I love cooking.
All right, ladies and gentlemen. For the record.
I love cold chicken.
Okay. Good for you.
I love cold mashed potatoes. I do not like cold mac and cheese.
Okay. Again, all good for you.
Yes.
Wonderful. Excellent. Amazing. Incredible. All right, ladies and gentlemen. So today, got a question of the day for you. You do not have to actually do this job. Okay? But what do you think the coolest job to have would be? So it may not be something you're interested in doing, but what do you think would be the coolest job to have? Zoe?
Probably an artist.
An artist? Okay. Okay. Victoria?
Being an underwater welder. I think that would be
Underwater welder. Okay. Okay. Okay.
I think the cool job would be
Well, go ahead and share, Ethan. Go ahead.
a country singer.
A what?
Country singer.
Country singer. Okay.
I want to be a country singer.
Okay. Okay. What would be the coolest job to have?
Cleaning like skyscrapers.
What?
Cleaning like the skyscrapers.
Ooh, could never do that.
Cool.
No way. Not
That would be
me.
cool. That would be
Not me. Ooh. Okay, that would be that would be an interesting job to have. Yes. So,
I know.
Gianna, what do you got?
Whole bands, yeah.
I don't know. Something to do with underwater. I feel like you said welding.
Yeah, underwater welding.
What else can you do underwater?
What do you want to do?
I don't think that's okay.
Actually, I'm sure that there are those who lead people on like tours and things. So I guess that would kind of be a professional scuba diver.
People that just stay out in the wilderness and have you ever seen that people that stay out in the
A
wilderness?
survivalist.
Yeah, and then they give people tours of those people. So I could never.
Okay. Huh? Jazz.
A chef.
The chef.
Yeah.
Okay. Mariana.
See, Anna, look how cool that is.
Yeah, no, I see underwater well.
No cool job.
I feel like just
Okay.
Yeah, I want to be like an underwater train.
An underwater train driver.
Yeah.
Yeah.
Now, I agree, you can do a lot of things, but I don't know if they drive trains underwater.
I'll be the first.
Okay. You could be a submarine tour guide.
I
No?
want to be a train. I'll do a lot of trains.
Okay.
Don't we have the thing that isn't it a train that goes under the Atlantic towards
Yeah.
Europe?
Wait, let me just...
I got me there.
See, Mr.
Got me
Brand,
there.
they actually have underwater welding.
I know, and it's actually a very high paying job.
It's like $30 an hour.
I think it's even more than that.
Really?
Yeah. Yeah. All right, Alex, what do you want to do? Well, let me rephrase that. You don't have to do this job. What do you think would be a cool job to have?
Train driver.
Okay.
What?
Really?
Yeah.
Okay. Okay. Who knew? I didn't. Brianna?
Okay, but I won't do that.
What would be the coolest job you think you could have?
44.
Again, you don't have to do it.
44 is not a job.
No. Christian? Skydiving instructor. Okay.
Yeah.
Okay. Last summer, at the end of summer, right before we normally go back to school, my brother and brother-in-law and I, we get together and we go golfing somewhere near the border. And the golf course that we were at was right near a skydiving place. So literally, as we were golfing all day long, you'd see the plane go up, you'd see the people jump out, their parachutes come down, see the plane land, and go back up again all day long.
You didn't do it?
Heck no, I was busy golfing, which was a lot safer because I kept both feet on the ground. So, no. Actually, I wouldn't mind skydiving. I'm not a big fan of heights, but that would be the one thing I would try to overcome my
Me
fear
and
of
my
heights
dad are trying to do it for my 18th birthday.
Okay. All right. Jimena, what would be a cool job to have? You don't have to actually do the job, but what would be a cool job to have?
Detective.
A detective? Okay. All right. Miss Art? Okay. I think one cool job that I would like, and again, you don't have to like, but I think a cool job would be a lawyer. Get to argue all the time. I want to be the courtroom lawyer. I don't want to be the person doing the research and all that other junk. I just want to be the one arguing in court.
What about a judge?
Judge would be pretty cool too. Sit there and decide things. Plus, I would just love to just once be a judge, and when these people bring stupid like lawsuits, be like, "You're out of here, dude. And you actually owe us money," instead of suing to get money. The other thing that I think would be a really cool job would be like a stadium announcer to announce like baseball games or football games or basketball games. I think that would
do
be.
that at my uncle's baseball game.
See, I think that would be a cool job. I think that would be a cool job to have. All right.
They make $44 an hour.
Well, especially too. But you think about it. If you were to go with a baseball team, you get to travel to because you get to announce their games on the radio or whatever. That'd be kind of cool. All right, ladies and gentlemen. Let's talk about where we're at today. First of all, thank you very much for doing the lab and turning it in last week. I got all but 2 labs turned in from you guys. I got them graded. I got them back to you. Nice job with that, ladies and gentlemen. We're going to take a minute in just a second to look at the last couple questions on there because it's not that you did a bad job on it. I just want to go over those 2 questions to give you an example of the way you can answer a question 2 different ways and still be right on it. So we'll talk about that in just a minute. Today, that Half-Life Lab worksheet is due today. I will tell you there are questions similar to it on the test tomorrow where you are going to have to figure out some Half-Life stuff. I got a Quizlet for review already out there for you, and then we'll take a look at the study guide for the test tomorrow and review for it and tell you what's going to be on the test. So those are the things that we have going on, ladies and gentlemen. Those are the things that we will get done today. Again, So here's where we're at, ladies and gentlemen. We are in week 9, okay? And there are only 13 weeks to this trimester, okay? We're in week 9. There's only 4 days this week. There's 5 days this week. Well, again, unless we get a snow day, there's no school this week Friday. So, 5 days next week. 4 days the week after because you guys are off on Friday. 4 days the week after that because you're off on Monday. And then this is the week of finals, which means that in the last couple days of that week will be the half days when you're taking final exams, and you'll get out early. So that's it.
And do we have a final in here, or is it just a test?
There will be, well, it'll be a final exam test. There'll be the Unit 8 test, and then there will be a final exam as well. Okay? So keep that in mind. Questions? What's
I
that?
was telling Mr. Nelson, he made us do like a whole big poster for his lifespan class or whatever it is. Yeah.
Biology?
Yeah, biology.
Okay, good.
I have biology with Mr. Brent. It was
Okay.
whatever it was, life science or whatever.
Well, biology.
Biology.
Yeah, it's biology. Okay. So you take physical science and you take biology, then you get whatever one you want after that. So, okay. Okay. All right. And he made you make a poster about your life?
No, just like how just lifespan of like different animals.
Okay.
We had to do that, I think.
Mr. Brent, is it possible I can go to the library to get a new computer charger?
What's that?
Can I go to the library to get a new computer charger?
A different one or?
A new one, because I plugged it into my outlet, and that's what happened.
Oh yeah.
Try.
Hold on, this
Yes, but does it still charge?
one. Yeah.
Oh, then that's fine. All that happened was you created a little short circuit. Not a big deal. It'll still work. If it doesn't, let me know and then we'll talk about sending it out. All right. Real quick, before we get working on our stuff for today, ladies and gentlemen, I would like to take a look at the questions that we did in the lab. Okay? Not necessarily the first two, because you pretty much did those really well, ladies and gentlemen. The second one, where you are asked to make a decision, which set of data provided the most convincing demonstration for your notion of half-life and why? When you're given a choice, ladies and gentlemen, you can make a decision based on what you decide is the most important thing. But what I ask you to do is go back to this chart up here, ladies and gentlemen, and take a look at it. Now, again, if you're going to tell me that your numbers, remember, we were comparing this to a perfect set. So 80, 40, 20, 10, 5, correct? That would have been perfect, okay? These numbers don't come out perfect. Now, if we take a big enough sample size, sometimes they will get really, really close. And yours weren't bad. This one was off by 2, this one was off by 3, this one was off by 1. The main thing is when you make a decision and you say, my data was closer, don't say because I think it was closer. I know that you think it was closer. That's why you picked it. What I would want you to say is, okay, in my set, two of the 4 numbers were perfect as far as it was 20 and 5. Okay? Or this was off by 2, this was off by 3, this was off by 1. So that's a total of being off by 6 on this set. In my set, we were only off by 5. I was off by 2, 1, and 2. Something like that. But you've got to justify your reasoning with something more than just because I think it is. Okay? Now, the two that I do want to talk about are the last 2 questions, ladies and gentlemen. By the way, this one, a lot of you did it really well. But then some of you forgot to tell me what the answer was. Because we did this table so that we could find after 4 half-lives how many were left. Most of you did that correct and did a good job with it. By the way, I did see a couple people who, for some reason, they took this 0 out and put a 1 there. And then they went down and it made all their numbers off by 1. So just be careful with things like that. Okay, ladies and gentlemen, be careful. All right, this was the question, the first one that we talked about a little bit last week, but we didn't seem to, well, I said you could give me either answer. Let me explain what I mean. The idea of half-life is that if you have a sample, half of it will decay over a certain period of time. But that also means that if half decays away, how much is left? Half. So should you ever run out of something based on the idea that you're taking away only half each time? No. And if you wanted to, that could have been your answer. No, you should never run out because half will always be left. And that is true. Half should always be left. Okay? But
Doesn't it?
Go ahead. Go.
Doesn't it depend on the object though?
What do you mean?
Like, say coffee, like that's gonna run out after so many drinks.
Okay, but not technically if you're only taking half. Now, it may get... This is the other way you could have answered the question. Yes, it will never, or no, it will never run out because always half will be left. But the practical part of this, that is the theory part. The theory part says half should always be left. But the practical part says this. Eventually, you get to such a small amount that it's like it's gone. Okay? So we talked about taking a piece of bread or drinking half of your soda, then drinking half of what was left, then drinking half of what was left. Eventually, you're going to get to the point where there's only a little bit left. And you probably can't divide it to where you can divide it or split it in half, right? So then you got to drink the last of it. Okay? So that is another way you could have approached this. Think about the lab. If you kept shaking the box, you would eventually probably got down to 1 penny, correct?
Mm-hmm.
Well, what happens when you get down to 1 penny?
You shake it again, it flips. Do you know how to more?
Eventually, one time you're going to shake it, it's going to flip and it's going to be gone. And you're going to be like, I have no more sample. And that is what happens in real life with radioactivity. It gets so small a sample that we can't detect it anymore. Now, it may still be there. There may be a few atoms up. Because remember, atoms are really, really, really tiny, right? Mm-hmm. We're looking at large amounts of them. Okay? So when you talk about your can of soda and you're getting down to the last of it, there may only be a drop or two left in there, but that drop actually is made up of probably thousands upon thousands of tiny molecules. Okay? So we could cut that in half. We wouldn't be able to see the amount there. We could cut it in half again. We still wouldn't be able to see it. So in reality, ladies and gentlemen, the idea of half-life is that you should never run out of something. You should never run out. Why? Because there should always be half left. But the practicality of it is that a sample gets so small that it's like we can't see it anymore anyway. So it may still be there, but we can't detect it. We can't notice it. We can't see it anymore. Okay? So that's what I mean when I say you could have answered this either way. Your answer could have been, we will never run out because you will always have half left. Or we eventually get to the point where our sample is too small for us to notice, and then it's like it is gone. So either one of those would have been acceptable. And the last one, ladies and gentlemen, in this simulation, is there a way to predict when a particular penny will decay? Must be more than a yes or no for credit. Explain why or why not. Okay? Well, you were right when you said it is a 50-50 chance. It is. Okay? So is there a way of predicting when one individual penny in that sample would flip? No, there isn't, because it may never flip. It could be the last penny you have in there shaking the box and it's still not flipped. It is possible that it could make it all the way through your experiment and never flip. It is possible it could have been the first one to flip. With radioactive decay, we cannot predict when an individual penny will flip. We can predict the rate at which they will flip. In other words, every time we shake it, about half of them flip. Which ones we don't know, but we do know that about half of them will flip. Okay? And that's the same thing with atoms. You cannot look at an atom and go, that atom is going to decay any second now. No, it may never decay. It may never decay that we know. Or it might be the first one to decay. There's no way to predict it. But what we can predict is when we get a large sample of those atoms together, that after a certain amount of time, half of them will decay away. Okay? Yes, sir.
How long do atoms last?
How long do atoms last? You can't destroy them. Law of conservation of matter. You cannot create or destroy matter. But what we're talking about is, remember, during a radioactive decay, during nuclear decay, it's not that this atom doesn't exist anymore, but certain isotopes of it become a different element. That's what we're talking about. We're talking about this atom of uranium-235 becoming thorium-231. Okay? And when that happens, the amount of this goes down. It goes down. Okay? Now, overall, we've changed what atom is there. But if you think about it, the protons that were in the nucleus are now in two different places, but they're still there. We didn't destroy it. We just changed it into something else. Okay? You cannot destroy matter. Okay? The water that we have on the planet now has been around since the planet was formed. Now, it may have been in a lake, it may have been in a river, it may have been in a stream, it may have been in someone's body that they had a drink. And then eventually, as their body decomposes after death, that gets back into the environment, back into the atmosphere. Okay? But the water that you're drinking now is the water dinosaurs peed in 1 million years ago. Okay? It is. Okay? Yes, keep that cheery thought in your head the next time you go get a drink of water out of the bubbler.
Is that why we purify our water?
What?
Is that why we purify?
Well, we don't even have to purify. Nature does it. Okay? I live outside of the city of Green Bay. My water comes out of the ground, out of a well. And as rain hits the surface, it will go through the surface through layers of rock and stone and sand and things like that. And then it'll accumulate in the earth, and it's pure enough to drink because it gets purified on the way. Okay? The water that you pee in goes to Green Bay Waste Management. They take and they clean it. Then they put it back into the environment. Why? Otherwise, what would happen? Think about it. 7 billion people on Earth, every time they peed, they flush a couple gallons of water. We'd be running out of water to drink. Right? We would be. But there are ways of cleaning it. It's been happening for billions of years. It's going to continue to happen for billions of years even after we're gone. Okay? Now, in some areas like in California, they've had to find ways to speed up this process because they're in extreme drought conditions, and that's not a good thing because that means there's not as much water in the ground for them to pull out and drink and things. But again, it's all gets recycled. The matter that we have here on Earth has been here forever. There isn't any new stuff being made. The matter in the universe is the matter in the universe. Okay? We're not making any more. We're not losing any. In a nuclear reaction, some changes. But please remember this, too. The uranium-235 could decay away into thorium-231. But it's possible that some other element could be decaying down into uranium-235. So, again, things are changing, and maybe the amounts shift a little bit, but overall, the matter that we have here on Earth is what we are always going to have. Always. Okay? Questions? So even when plants and animals take in carbon from the ground, carbon dioxide from the air, water vapor from the air, and then they die, they release it back eventually. So, okay? All right, that takes care of that, ladies and gentlemen, for us. All right? So let's take a look at the study guide for today, ladies and gentlemen. So this is in your EIS or in your Google Classroom. Here's the study guide for today, ladies and gentlemen. Okay. So let's start with the topics. Okay. Because we are on the nuclear unit, we began with the structure of the atom, the protons, neutrons, and the electrons. Now, which of these parts did we kind of ignore? Nope. Nope.
The protons.
Nope. Good. We were 1 out of 3. Third choice, yes. We ignored the electrons because we don't really care about them. Those are involved in chemical reactions. Those are not involved in nuclear. But we talked about how the protons could change and it could become another element. We also balanced off the neutrons when that mass number was 4 at the top. Okay? So we accounted for those. We looked at nuclear symbols. By the way, a nuclear symbol would again look something like this. Nope. Nope. These are the nuclear symbols. The element here.
Oh, yeah.
By the way, this is not, don't look for X on the periodic table. There is no element X. This would be Z naught. Okay? This is the atomic number. This is the mass number. We subtract these two. This is the number of neutrons. Okay? And we got all that information from that one symbol, ladies and gentlemen. Okay? The nuclear vocabulary, know what radioactivity, nuclear decay, photon, and quantum are. Photon and quantums are bundles of light energy and bundles of electromagnetic energy. Why did we talk about electromagnetic radiation? Because radiation is energy traveling as a wave. That's what nuclear reactions give off. Okay? We talked about the 2 types of waves. We talked about the parts of a wave, the crest, the trough. Wouldn't surprise me to see that diagram that you already saw in quiz 1 back again, ladies and gentlemen. Just telling you. Talked about wavelength, talked about frequency, talked about energy, talked about the relationships between these 3. If the wavelength goes up and the frequency goes down, what kind of relationship is it? If the wavelength goes up and the energy goes down, what kind of relationship is it? And if frequency goes up and energy goes up, what kind of relationship is it? We talked about the 3 different kinds of radiation. Now we're into those Greek letters. Now we're into their alpha, beta, and gamma. Okay? We also talked about ionizing and non-ionizing. So that went back to the electromagnetic radiation and talking about how ultraviolet, X-rays, and gamma rays were the 3 types that could hurt us. But infrared, microwaves, radio and TV waves, visible light, those do not hurt us. They are non-ionizing. We talked about nuclear reactions. What happens to the change in the atomic number? What happens to the change in the mass number? During alpha decay, during beta decay, during gamma decay. We talked about radiation exposure and what will happen if you are exposed to radiation, ways it can affect you, what it can do to your health, things like that. And we talked about half-life, ladies and gentlemen. We talked about half-life. We talked about terms like fraction remaining, sample size, half-lives, the time it takes, all of those things. So those were the topics that are going to be on your test tomorrow, ladies and gentlemen. Questions? And here's the good news. Then we got 1 more unit to go. That's it. 1 more unit to go after that. The last one is, it's called industry, but it's basically a lot about the periodic table and practical uses of things. So that's what we're going to talk about in the last unit. Questions? Okay. So, ladies and gentlemen, after this, in your notes, there is a review. So again, when you're doing the review, the reason that the review is there, ladies and gentlemen, is if you look at this question and you cannot answer it, you better put something down on your periodic table to help you remember that. Because these are the things that you are going to be asked during your test. So what are 2 ways that nuclear and chemical reactions are similar? What is a way that they are different, ladies and gentlemen? Okay? Name 2 ways that electromagnetic waves differ from mechanical. So what is there about an electromagnetic wave that is different from a mechanical wave? Name 3 types of ionizing radiation and 3 types of non-ionizing radiation. Explain the difference between wavelength, frequency, and explain the difference in energy wavelength and frequency between ionizing and non-ionizing. In other words, ladies and gentlemen, for here, let's keep it simple. Shorter and longer. Are shorter wavelengths ionizing or are shorter wavelengths non-ionizing? Frequency, high and low. Is low frequency ionizing or is low frequency non-ionizing? Energy, high and low. Is high energy ionizing or is high energy non-ionizing? You should be able to put them together based on which ones are ionizing and non-ionizing and what happens to these 3 things as you move from one end of that spectrum to the other. Okay? So, differences between alpha, beta, and gamma decay. And then a couple similarities. Lots of differences available, ladies and gentlemen. By the way, the differences should be between at least 2 of them. If these 2, for example, have the same change in mass number, but this one has a different change in mass number, you could still put it down. Okay? You could still put it down. All right? So differences between the 3, at least a difference between 2 of the 3 of them. Okay? And similarities, things that are the same in all 3. Tell 2 differences between longitudinal and transverse waves. The 2 parts of each kind of wave. Rank the types of radiation based on strength and ionizations. What is the strongest? By the way, here I'm talking about alpha, beta, and gamma. Okay? Number 9 is the table like we've been doing. Okay? And then there's a spot for you to answer the question. Number 10 or 9, 10, 11, all of those are the same. Here's your relationships down at the bottom. Questions, ladies and gentlemen? Okay, so you have got a good 35 minutes here. Okay? You have got Quizlet to work on. If you're finished with this, you've got this to work on. If there is something that you are missing from the unit. Now again, the only thing out of these things that counts toward your grade is this one right here. That is the only one of these. But if you want to do some of these others because you want to practice on them before the test, get them done, ladies and gentlemen. Get them done. Questions? All right, ladies and gentlemen, go to work. If you need me for something, please let me know. I will be happy to help you.
Can we listen to music?
You certainly may.
I thought you were going to say you certainly may not. Oh my God.